Howdy do. For a large part of this course, we've been looking at derivatives. And one fact about derivatives I'd like you to recall is that the derivative of a function at a point is the slope of the tangent line to the curve at that point. And we originally calculated this by looking at secant lines and taking a limit. I want you to recall this because we're going to see a parallel moving forward. The second big portion of calculus has us looking at integrals, and we're going to see that integrals stem from a geometric limit as well. To see this, what I want to do is begin by examining the area underneath a curve. So here I've given us some x and y axes. And what I want to do is I want to look at a curve from some function y equals f of x, and I want to look at the interval from a to b. So we're looking at a function very specifically on an interval. And what I want to do is I want to talk about this region in here, which we can call S. That is basically the region underneath the curve and above the x-axis in between those two values. I can't shade it in perfectly because the width of my little highlighter is a little bit bigger than this area up here, but if you'll forgive that, we've got this region, and it is between the x-axis and the curve, y equals f of x, and we're looking from a to b. So this line segment over here is part of x equals a, and this other one is part of x equals b. And so we have this region that's bounded on the left by x equals a, on the right by x equals b, on the top by the curve y equals f of x, and the bottom the x-axis. And we want to find the area of this region. And in general, we want to develop a method that will allow us to find the area of regions like this that are bound by a curve from a function and the x-axis and then two x values. So that's kind of the problem that I want to talk about today. I want to talk about how we can maybe figure out a way to either calculate this area or to approximate this area. Now, in solving this problem, we have a very intuitive definition of what area means, but usually in previous math classes, when you were calculating the areas of regions, you were looking at regions that had straight lines, and in those cases, areas were pretty easy to calculate. If you had some sort of a rectangle, we know that the area of a rectangle is the length times the width. Or you could say the base times the height. Really doesn't matter. There's different ways to refer to that same thing. If we have a triangle, for example, we know that the area is 1/2 the base times the height, right? And then we can look at other shapes. It would take too long for me to draw these as actual straight lines, so just pretend that these are straight lines. But if we had a shape that wasn't an easy one that we knew how to deal with, what we could do is we could break it down into triangles. And we could calculate the areas of each of those triangles if we knew the bases and the heights. There are also formulas if you know all three sides of a triangle, and we know that the total area is the sum of the areas of those regions. That is a strategy that we could use if we had kind of a weirder shape, but it still had straight edges. We could break it down into triangles and figure out the area that way. Now, unfortunately, what we're looking at over here, we cannot easily represent it as a rectangle or a triangle, or even break it down into triangles, because one of the sides of this, or one of the boundaries of this, is a curve, not a straight line. So it ends up being a little bit more difficult to figure out the area. This is something that we will develop over time. But what we can do is we can come up with an approximation. And we can come up with an approximation by taking the region and chopping it up into strips. And for each of those strips, we can use a rectangle to approximate the area. Obviously, this is not perfect, right? This is not an exact answer because we can see all these extra little bits, but it does give us an approximation. And we're going to start with that and then see if we can use that to develop ways to get better approximations and eventually figure out the answer. So let's actually take a look at a real example now instead of just this generic function. What I want to do now is I want to look at the function y equals x squared plus 1, and I want to find the area underneath this curve, specifically between 0 and 1 for our x values. Now, the way that we can estimate this, as we just saw, was we can cut this up into rectangles. And what we're going to do, I'm going to cut it into 4 rectangles. So I'm going to draw 3 vertical line segments. So we've got 1/2, 1/4, and 3/4. Hopefully this is not that scary so far. And then what we're going to do is we are going to use rectangles to approximate these strips. Now we have choices to make. We can, like if we wanted to look at this one, to use a rectangle to approximate it, we could use a right-handed rectangle, meaning we are using the right endpoint to figure out the height of the rectangle. That's going to be an overestimate. We could also use the left one to approximate that as a rectangle. That's going to be an underestimate. Neither of these is going to be perfect. And so what I'm going to do is I'm going to use the right side. So let's use right-handed approximating rectangles. So we have 4 rectangles here. One that spans the interval from 0 to 1/4, one from 1/4 to 1/2, one from 1/2 to 3/4, and one from 3/4 to 1. And we know that the area of a rectangle is base times height. In each of these, the base has a length of 1/4, and then the height is the y value or the function value on the right-hand side of the strip. So what I'm going to do, I'm going to call this R4 because we're using 4 right-handed rectangles as an approximation. And so we know that this first one has a base of 1/4. They all have a base of 1/4. And then the height is the function value on the right-hand side of that strip. So that's f of 1/4, or we can say 1/4 squared. And then when we look at the next one, the base is also going to be 1/4. And then the height is this value squared, so 1/2 squared. And then the third one also has a base of 1/4, but the height of that is going to be 3/4 squared. Because remember, the height, the y value, is x squared, and we use the right-hand side there for that rectangle. And then this last one, can you figure out what the area is going to be represented by? It is 1/4 times 1 squared. And already these videos are going to be long, so I do not want to take the time to do all of these calculations by hand and make them longer. So I'm just going to tell you that if you were to get a common denominator and add all of these together and reduce, you would end up with 15/32, which is equal to 0.46875. That would be our right-handed approximation of the area using rectangles. Now the question is this an overestimate or an underestimate? And in this case, it's an overestimate because it's including all of these extra bits. in our area calculations. So if we want that, this is kind of an upper bound for what the area could be. We know that this is an overestimate, so we know the area is something less than this. If we want a lower bound, an underestimate, we could use left-handed rectangles. So we could use kind of the left end point for each of these. And then for this interval, it would be that rectangle. And then for this one, it would be that. And then for the left one, there'd be no height because it's 0. And we could do the same sort of a calculation. The base is still 1/4, but then when we're calculating the height, we're using the left-hand sides. So it's going to be 0 squared for the first one, and then 1/4 for the second one, right? This is a height of 1/4 squared. And then the next one is going to be 1/2 squared. And then the last one is 3/4 squared. And again, I don't want to take all the time to do these calculations. I'm just going to give you the answer. That becomes 7/32, which is 0.21875. So both of these are approximations for the area. They're very different numbers, so they're not great approximations because the right-handed rectangles included too much area, and the left-handed rectangles didn't include enough area. It kind of cut out things. So in the end, we know the area is actually between these. We can say 0.21875 is less than the area, which is less than 0.46875. So we know the area is in between these two numbers. Those are both approximations for the areas, but it's somewhere in between those. Now, the question is, what can we do to get an even more accurate approximation? And there are several things that we could choose to do. One of the things that we could do, instead of using left endpoints or right endpoints, we could use midpoints. We could say, for each one of these, you take the middle point in the interval and you use that to figure out what the height is. So you could use rectangles where you take the height from the midpoint. And if you happen to do that with this problem, you would get 0.328125, which is in between these two numbers, and it's probably a better approximation because you can see if we use this rectangle, it's not going to be way too small. It's not going to be obviously an undercount. And like the other one, it's not going to be obviously an overaccount. It's going to be somewhere in the middle. So this is going to be probably a better approximation than either of these two. One downside of using the midpoints is that we don't know if it's an over-approximation or an under-approximation. So yes, it does give us something that's better, but how much better? Not quite sure. In the end, the answer that we really want to go for is we want to use more rectangles. We only used 4 rectangles here. And when we did that, we had a whole bunch of extra bits that we were calculating for the area if we were doing it with right-handed rectangles. And with the left-handed rectangles, we were undercounting by quite a bit. And if you use more rectangles, you're going to get more accurate estimations. I'm just going to tell you, if we used 10 rectangles, 10 right-handed rectangles, the approximation we get is 0.3984375. And if we use 10 rectangles on the left to approximate, we get 0.2734375. So already you'll see that these numbers give us a much smaller range than what we had when we had 4 rectangles. And if you were to go on and use 1,000 of them to try and be much, 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 much more accurate, your right-handed rectangles would give you 0.33383335, and your left-handed rectangles would give you 0.3328335. And we're starting to see the results that we're getting are getting closer and closer and closer together. And in fact, there is a limit when we take the number of rectangles to go to infinity, and that is how we define the area. The area is the limit as n approaches infinity of r sub n, meaning the area that we get when we separate it into n strips and use right-handed rectangles as approximations. And this is equal to the limit as n approaches infinity of L sub n, that is the left-handed rectangles. And you will see that these two limits, assuming they exist, are equal to each other, and that is how we define the area. Looking at these, can you guess what our limit might be? There's a very nice number that these are getting closer and closer to. When we started with 4 rectangles and went to 10 and went to 1,000. Well, these are all approaching 0.333333333, repeating, which is 1/3. And in fact, the area of that region is actually exactly 1/3. And that is how we figure out the areas. We can define it as a limit of the sums of these areas of approximating rectangles as the number of rectangles goes to infinity.